The packet fragmentation handler is a low-level network component responsible for dividing large datagram payloads into transmission-sized units. The system maintains a configurable maximum transmission unit value, defaulting to 1500 bytes for standard Ethernet frames. Fragment generation occurs at the egress stage, after payload serialization but before protocol header attachment. All fragments retain references to the original packet identifier for reassembly at the destination. Fragment ordering is preserved through a monotonically incrementing sequence number field, independent of the main packet sequence counter. Each fragment header contains an offset value indicating its position within the original payload, measured in 8-byte units from the beginning. The more fragments flag is set in all fragments except the final one. Payload length in the fragment header reflects only the data contained in that specific fragment, not the original packet size. Fragmentation occurs only when the payload size exceeds the MTU-protocol header overhead. Header overhead calculation includes IP4 or IP6 headers, optional extension headers, and transport layer headers. For standard configurations, payload threshold is 1460 bytes on IP4 networks and 1440 bytes on IP6 networks with standard headers. Fragmentation does not occur for packets marked with the Do Not Fragment flag if they exceed MTU. Instead, an error condition is generated. The fragmentation buffer maintains state for each active fragmentation operation. Internal state includes the original packet metadata, creation timestamp, total fragment count, and a bitmap tracking received fragments. Buffer entries are automatically pruned after a configurable timeout period, defaulting to 30 seconds. Timeout is measured from the timestamp of the first fragment reception. Early cleanup occurs when all fragments have been received and reassembly is complete. Fragment reordering is handled automatically during reassembly. The system does not require fragments to arrive in sequence order. Out-of-order fragments are stored in the reassembly buffer according to their offset values. When a gap is detected in the offset sequence, the handler marks the packet as incomplete. Once all fragments have arrived, the handler concatenates them in offset order to reconstruct the original payload. Duplicate fragment handling is performed through offset-based comparison. If a fragment with an identical offset and packet ID is received twice, the system discards the duplicate silently. No error condition is generated for duplicate fragments. The bitmap tracking mechanism ensures that overlapping or out-of-sequence fragments do not cause reassembly errors. Fragments with partial offset overlap are rejected and logged. MTU discovery is performed through a separate subsystem that operates independently of the fragmentation handler. The discovery mechanism sends probe packets of increasing size and monitors for fragmentation required or unreachable errors. Discovered MTU values are cached per destination IP address with a time to live of 10 minutes. Cache entries are automatically invalidated when an error condition indicates path changes. Path MTU caching is disabled by default for security reasons. When enabled, the cache stores MTU values keyed by destination address without transport layer port information. IP4 and IP6 caches are maintained separately. Cache memory usage is bounded by a per-entry limit of 128 bytes. Maximum cache size is configured at initialization, with a default of 1024 entries total. Eviction follows a least recently used policy. Error handling in the fragmentation handler follows a consistent pattern. All errors are logged with severity level and packet identifier. Invalid fragment headers trigger a discard operation with logging at level 3. Missing fragments after timeout trigger reassembly failure notification to the higher layer handler. No exception propagation occurs. Instead, the handler transitions to a terminal error state and cleans up resources. Fragmentation statistics are maintained in a read-only registry accessible via standard telemetry interfaces. Counters include total fragments transmitted, total fragments received, reassembly successes, reassembly timeouts, and duplicate fragments discarded. Counters are 64-bit unsigned integers that wrap at maximum value. Statistics are reset at system startup. Per destination counters are not maintained due to memory constraints. Memory allocation for fragmentation buffers uses a pre-allocated pool strategy. The pool contains 256 buffer objects of fixed size, with each object able to store up to 16 fragments. Allocation is performed at system initialization and never occurs at runtime. When all pool objects are in use, new fragmentation requests are rejected and logged. Pool utilization statistics are available through the telemetry interface. Reassembly completion detection uses a simple algorithm comparing expected fragment count against received fragments. Expected count is calculated from the offset value of the final fragment. If the final fragment offset plus its payload length does not equal a multiple of fragment size, padding is assumed in the final fragment. Reassembly is marked complete only when all expected offsets are covered by received data. The reassembly callback mechanism allows higher layer protocols to register handlers that are invoked upon successful reassembly. A maximum of 8 callbacks per packet ID is supported. Callbacks are invoked synchronously in registration order. If a callback fails, an error is logged but subsequent callbacks are still invoked. Callback registration occurs at packet creation time, before fragmentation. Configuration parameters are specified at system initialization in a structured configuration object. Key parameters include maximum MTU value, fragmentation timeout interval, buffer pool size, and reassembly callback limit. Configuration is immutable after initialization. Attempting to modify configuration at runtime returns an error status. Default configuration values are suitable for standard network environments and rarely require tuning. Integration with transport layer protocols occurs through well-defined callback interfaces. The fragmentation handler provides hooks for payload ingestion and reassembly notification. Transport protocols implement handlers that process reassembled payloads according to protocol specifications. The handler itself does not interpret payload content. All interpretation is delegated to higher layers. Separation of concerns maintains modularity. Shutdown and cleanup operations are performed through an explicit close function. The handler flushes any pending reassembly operations and discards incomplete fragments. All buffer pool objects are deallocated. Statistics are preserved in memory for post-mortem analysis if required. The handler transitions to a closed state and rejects any further operations. No resources remain in allocated state after successful shutdown.